Okay, in this video we want to demonstrate how to actually use the chi-squared calculation. What do we actually do with this formula? How do we actually use it? So, what I've done is I've watched the orange tube video and I used my cell phone. So the idea is that at each position, all right, at these positions that are recorded on your lab write-up, right, we want the times from the origin. Okay, we want the times from the origin. So there's a few different ways you can get those. Number one, you can watch the video several times, time it from the origin up to the first piece of tape, go rewind it, time it from the origin to the second piece of tape, and so on. Or you can do what I did, and I used the lap button on my cell phone, right? So the time in between the origin and the first piece of tape was this measurement in seconds. The time measurement for the second measurement was here, between the first and the second, and then the time between the second and the third was here, and so on and so forth. So if I wanted the total time from the origin to each successive point, then I need to add these up, right? So the time here is, of course, just the time from the origin to the first point. The time here is the sum of these two, because this is the total time it took to get to the second point. My third position, or my third time rather, is the sum of all of these. This is the time it took to get to the third point. My fourth time is this total time, all of those, and my last time is all of these, right? So we have this data set, right? And I'm going to plot it. I'm going to go up here to Insert, Chart, and that's linear. That is pretty linear. So we are going to, I'm going to expand the screen here a little bit. Well, it'll be cutting off here in a minute. But anyway, I'm going to put a trend line on here, and we covered trend lines in the last video. So if there's anything over here on the screen you can't see, then you can go back and watch. It looks like everything you need to know is going to be in your screen. So we choose the linear option, and then of course we come down here to display an equation on chart and the R squared value. So again, the equation is the linear equation that best fits this line. Now let's interpret this equation a little bit, right? So our y values, the values on the y-axis, are our positions, right? Our positions. And on the x-axis here, we have the times. So we have positions and we have times, and we want to know what this slope represents. Well, if we come over here, right, if we start with this equation right here, we can write the equation of velocity. Remember, velocity equals delta x over delta t. And if I solve that equation for the final position, then I get this equation. And I can rewrite this equation. I'm just going to switch the ordering of the v and the t and the xi, and I get this equation. Okay, so I get xf equals vt plus xi, and we see that this has the form of a linear equation, y equals mx plus b. And so y is my variable, my dependent variable rather. The velocity v represents the slope. So the slope of my graph here, whoops, wrong one, here we go. The slope of my graph here, 6.3587, represents the velocity that the bubble in the tube is moving with. And so that's why plotting is such a powerful tool, because it allows you to draw physical conclusions. I don't have to measure the velocity directly to actually calculate it, okay? So what we would say is that the velocity of the tube is 6.3587. And one other thing you can do is perform a linest function. And if I perform a linest function on the data, this will give me the uncertainty on the velocity, right? Remember to Control-Shift-Enter, and here we go. So there's my slope and my uncertainty on my slope. So if I were going to round this to maybe 2 decimal places, then I would say that my value is 6.36 and that my uncertainty is 0.08. Okay, because if I round this to 2 decimal places, then the digit following the 5 here is bigger than a 5, so I have to round up. And the digit at the 7, the digit after the 7 is a 5 or more, so I also have to round that up. So what we're saying is that my velocity is going to be 6.36 centimeters per second plus or minus 0.08 centimeters per second. So it could vary anywhere between 6.44 and 6.28 centimeters per second. Okay. All right. Now, what about the funny chi-squared business? All right. What are we doing? Well, let's go back here to the equation. Right. So here is a predictive model. All right. This is our model. If I know what the velocity is, and if I know what my intercept is, then I can compute or predict the final position, or where the final position should be at any given time. So essentially what we are going to do is we are going to set the intercept to be the intercept given in Excel, but we are going to find the velocity that allows our predicted positions to best agree with the observed predictions, right? So our observed predictions are these positions right here. We tried to get as close as we could to the 10, 20, 30, 40, and 50 centimeter marks. And one other thing we need is the uncertainty on these, and in general, they're going to be pretty close to each other in magnitude, and usually they're a fraction of your actual measurement. Now, one way to estimate the uncertainties here is notice that this value is a little bit shorter than the rest of these. So that means I may have hit the button a little early, and that means that the position may be off somewhat by a larger amount than most everything else. So what I'm going to do is I'm going to format these cells, and I'm going to take them out to 2 decimal places. All right, and I'm going to give this one an uncertainty of 5 millimeters or 0.5 centimeters. Okay, remember these are in centimeters. And the rest of these are pretty close. This one's a little more off, so I'm going to give it a little bit higher uncertainty. But in general, a couple of millimeters is okay. So I'm going to leave these as about 0.2 for each of these. And then I'm going to give this one, since the time is a little smaller than the average in here, I'm going to give it about 0.3 centimeters. All right. So those are my uncertainties. Now, one thing that we need to note is that when we come over here to this chi-squared, that the way Excel actually computes this equation, the way that Excel fits the data, is actually based on this process. It goes through it a different way, but the process is essentially the same. So I'm going to copy and paste these data here and put them into the data here. And oh, whoops, that's because these were formulas, and so when you copy and paste formulas, they don't always work. So what I want to do is actually copy and paste the values. So when I come over here, I'm going to paste the values. Oops. There we go. That's what we want. Okay, so this is our position measurement. This column represents our calculated position, and notice that the formula is already in there, right? Our formula is the velocity times time plus the intercept. And so what we have is we have the velocity. We're going to put the velocity here, and we're going to put the intercept here. And what we're going to do, what this calculation is going to do as we put things in, once we put the velocity and the intercept here, it's going to automatically calculate these positions, these predicted positions, and then this column is going to subtract the position, the measured position, from the calculated position. And that gives us a way to measure about how far off our calculation is from the actual measured position. But the overall formula, that big long nasty formula in your document, is actually wrapped up in these cells, and that allows us to also take the uncertainties into account. And that's the major difference between what we're doing now and what Excel does right here. Excel does not take the uncertainties on the individual measurements into account, and that's what we're going to do. So we're going to copy our slope and intercept, and we'll take it out to 2 decimals for the sake of time. So 0.81 and 6.36. So our intercept was 0.81, and our velocity was 6.36. Now you're going to take this out to 3 decimal places, and notice all of a sudden we have a number here. Okay. Now the question is, what happens to that number if I put a 5 right here? Ooh. Notice how this got smaller. So what we're doing is we're essentially comparing the measured and our calculated values, and we are summing up all of the differences between the calculated and the measured values. And so in theory, if your model is perfect, there should be no deviation. So in theory, if in a perfect world, if you hit the nail on the head, all of these would be 0. And so what that means is that this chi-squared calculation should be as small as possible. So you want to find the velocity that minimizes the chi-squared value. And notice, right, that even the difference between 6.35 and 6.4 produces a pretty drastic change in the value. So you shouldn't have, 6.35. You shouldn't have much trouble finding that point where the value is minimized. And it may take a little bit of moving back and forth between 2 values to see if it decreased or not. And it looks like we're headed in the right direction. So 6.33, let's try that. And it got a little worse, right? 6.34, let's go back here. And so it looks like to the nearest 2 decimals, 6.34 for the orange tube looks to be about the best. Now your task is also going to be to take this out 1 decimal further, right? So, for instance, if I add a 1 here, does it get any better or worse? And notice how small the change is. But in this case, it got slightly worse. So what if I try 3.9? Did that get better or worse? In fact, that got a little bit better, so then I would step that down again until I found the value out to 3 decimals that caused that to be minimized. Then that would tell me that that is the velocity. That is the best estimate for the velocity while taking these uncertainties into account. And that's what Excel does not do for you. So I wanted to expose you to this idea of building a model, right? Being able to then compare the model to your measurements, which again, in theory, if your model is perfect, you should be able to predict with 100% precision. But of course, in the real world, that doesn't happen. Uncertainties creep in, right? You may hit the button just a little early on your lap button on your cell phone. Or you may not have estimated correctly where the bubble was when you hit the button. So there's all sorts of reasons, even in a simple experiment like this, where uncertainty can creep in. And this is one of the methods that allows you to take those uncertainties into account when you're trying to measure something like velocity.